you can see the record of section C. They have recorded the whole lecture. Okay. So what we want to do today is, we want to introduce you with some representative signals in addition to what we have discussed in our earlier classes. Because you see that these type of signals are the very basic one by which we can analyze our system very easily, and we can reconstruct or construct our other signal using these representative types of signals. Okay, I hope you have some introduction about those things for continuous time case in electrical circuit 2 course. Okay, let us start with this figure. What is it?
A step function.
Okay, it is a unit step function. Okay, we call it unit step. The reason is that the step size is 1. If we generally define the step function, we usually define it in this way. Okay, this function has a value equal to a for time t is greater than equal to 0. Okay, when your a equal to 1, we call it unit step. Unit step function. Okay. Unit step function has many applications. We will show you after a few minutes. Okay. This is another version, DT version of the unit step. Just if we sample this function with a certain interval of time and represent it as a sequence of stems, then it will take this form. For the unit step where the magnitude of each of the stem will be equal to unit. After finishing this thing, I will be going to the whiteboard just to make further explanation on these two types of functions. Okay. Not only this, actually, let me go to the whiteboard just to discuss more about what is there in these few slides. Okay, it will be very helpful for you to understand. Okay, now you have your step functions. Okay, continuous time. You are just confining with say unit step. Okay, amplitude is 1. This is your UT. Now you see that we can shift our function. We can in either ways. For example, if we shift, for example, this unit step function in this way, UT minus T0. What does it mean?
The step function will appear at t equal to T0.
Okay, that means your function will be looking like this, isn't it?
Yes,
okay.
Sir.
Now, if you are going in the other way, then it will be something like this. Okay, if it is minus t, then your function will be equal to ut plus t0. Okay, even you can flip it. If we flip it, it will go in this direction. Then it will be equal to minus t. Okay, then you can again shift it to the left or to the right depending on your need. The same thing can be done for the case of discrete time unit step. In your discrete time step, these are the stems, something like this. Okay, then if we shift it, you have to shift it, for example, with finite numbers of samples. Okay, we start from n equal to 0, and if we start from n equal to 1, then this figure will be equal to u n minus 1, isn't it?
Yes, sir.
So depending on how many numbers of samples we are shifting or advancing, in this way you can write your equations. Okay, now we will be going to another function. We call it impulse function. Have you heard about it?
Yes, sir.
Okay, in which subject?
The Tripoli.
Circuit 2.
Yes. Yeah. Your impulse function is actually, you define the impulse function or represent the impulse function in this way. And it has a magnitude equal to infinity. Okay, when you are responding after someone is is it okay?
Yes, sir. Yes, sir. It is okay now.
So we usually represent our step impulse function in this way. It is a very localized function appearing at a particular instant of time. With amplitude, we represent it by an arrow. That means it is going to infinity. Okay, it can go in positive direction or it can go in the negative direction. Now, how this function is actually generated, what is the physical meaning of it, we will be just discussing on this thing. Okay, consider this function. Okay, unit step. If this is the unit step, if you want to take the derivative of this unit step, what will be the value?
So,
Bola, what will be the value? This is your function, okay? You want to take the derivative of it.
So 0, as it's a constant function.
Not constant, okay? Because you have a discontinuity there. I taught you in your first year, okay? Because your signal is changing from one point to another at most 0 time. Okay, this will be actually theoretically infinity at time t equal to 0, and it will be equal to 0 elsewhere. Okay, for this reason, this function is actually this function. Okay, roughly we can say that this is your delta t, the derivative of your delta function. Now this definition is actually very crude. If you want to understand it more precisely, then you have to start with this thing. Okay, consider that we are defining a step, a modified step, okay, approximate step function in this way, without, for example, making it going up sharply from 0 to 1 at time t equal to 0. We are telling that, okay, delta, it is taking delta time to go to the magnitude 1 linearly. So it will not be equal to a delta function. We are represented by this function, okay. When your delta tends to 0, then what will happen? U delta t will tend to what? U delta t will be tending to ut, isn't it?
sir,
So, can you take the derivative now? If you want to take the derivative dut, now d delta ut dt, how will it look like?
There will be a constant value from 0 to delta.
Okay, what is the value of that constant?
1
Constant.
by delta.
It will be equal to 1 by delta. There is any, this is actually the slope of your curve, isn't it? Then it will be equal to 0 elsewhere. Something like this. Your curve will be something like this, okay? Now you see that this is the derivative of this function. When, for example, say your delta is decreasing, say your delta, we are decreasing delta, then what effect will be there on this curve? Okay, if we enlarge this curve, something like this, this is your delta, this is 1 by delta, and this is this derivative. If we decrease delta in this direction towards 0, what will happen? This width will be decreasing, this height will be increasing, isn't it?
Yes, sir.
But the area of this curve or the area of your the letter curve that we have drawn will be remaining same. Delta multiplied by delta is equal to 1, isn't it?
Yes, sir.
And in this case, you consider this thing, where your delta is tending to 0, your UTT is going is nearly approaching your UT, then the derivative of U delta t and delta t is reaching towards the infinity, become the function delta t. But importantly, if we integrate, for example, this quantity, the derivative from dut by dt dt, or equivalently equal to minus infinity to infinity delta t dt, what will be the value?
So 1.
1.
Because this is the area of your curve, isn't it?
Yes, sir.
But the area will be remaining constant. Okay, this is what the basic thing you have to understand. That delta function is a localized function. Its amplitude will be infinity. It will be appearing at a particular instant of time, but its area under this thing will be remaining equal to 1. Sometimes in many texts, when we write delta t, a factor is multiplied with it, say k. That k is not the amplitude of delta t. The reason is that delta t itself is a function that magnitude has infinity, something like this. This is a delta t. When we multiply it with k, what is it actually? It is the area of your delta, okay? And that's why we do not call it area. Sometimes that k is called a strength of delta. A strength of your delta t, okay? Your delta t can shift in either ways, okay? Your delta can be there at this location, say this is your delta t. If your delta is shifted to the right at this location, say t equal to t0, then we write our delta as delta t minus t0. Similarly, when your delta is going to here, okay, say it is minus t0, then it will be equal to delta t plus t0. Fine. But the area will be remaining same, okay? Area of the delta function will be equal to unity. If we multiply that delta function, not multiply, associate this delta function with an amplitude, that is the strength, then area will be the strength of your delta. What is the utility of your function actually? This elementary function can be used to express any arbitrary continuous function of delta. How? That I will be illustrating in this figure, okay? This is very important for our purpose. Consider that we have a continuous function xt in t. Now initially consider the first curve, okay, this one. If we multiply, for example, these two signals, what will be the result of this multiplication?
There will be only a value at 0.
That means this point we will that means you are multiplying a signal xt with delta t. Your delta is at the origin. That will simply at the origin t equal to 0. The value of your signal is x0, and you are multiplying it by delta t, isn't it?
Yes, sir.
So and the value, yeah, but the arrow should be towards infinity. The reason is that delta itself is infinite, has infinite amplitude. So this x0 is appearing as the x0 is the value of your signal at the location of your delta, is appearing in the signal as the strength of delta. Similarly, if we go to this second delta, then you will have say another value of your signal at say x t0 with delta at delta t minus t0. Similarly, at this location, you have a delta, and the signal value will be equal to minus t0 multiplied by delta t plus t0, isn't it?
Yes, sir.
Okay, now the thing is that if we integrate, for example, any one of this function between these two limits, okay, consider this first one first. Okay, and assume that you do not have the left and right deltas. Then if we integrate, for example, minus infinity to infinity xt with delta t dt, we know that this multiplication is equal to what? Minus infinity to infinity x0 delta t dt. What will be the value? Because x0 is a constant with respect to t, it will be equal to x0, isn't it? Similarly, if we integrate minus infinity to infinity xt minus t0 delta t minus t0 dt, it will be equal to x t0, isn't it?
Yes, sir.
So in this way, this property of delta function is called shifting property of delta function. You can pick a value of your signal in this way from a continuous signal using delta. In many of our signal processing system, we need it for our case. But if this is the case, then if we make a running sum of x0 plus say xt minus t0 and many you just subdivide we are just considering a simple discrete instant. Rather than discrete, if we want to make it continuous shift, for example, we are shifting in this way, delta t minus tau. That means your tau is changing and your position of your delta is also changing. Then if we multiply, for example, a signal xt with delta t minus tau, what will happen? This will be equal to x tau, isn't it? X tau delta t minus tau, isn't it?
Yes, sir.
And your delta tau is actually, and you see that your delta is an even function with respect to origin, because if we shift, it will not change your position. Now, if we express the thing in this way, then if we integrate it, what will happen? We will be getting x tau, isn't it? So, in this way, if we integrate, for example, this integration minus infinity to any time t, and your signal value is x tau, we are multiplying it t minus tau and integrating it with respect to tau, then you will get your total signal, because you are simply, this operation is very similar to, you are simply taking your signal amplitude here, another amplitude there, another amplitude there, another amplitude there, and you are, all these amplitude are not appearing, for example, at a single instant of time. It is appearing in tau. It is variable. Then what will happen? All these things will constitute your signal. In this way, any continuous time signal can be expressed with the help of this integral. Okay, this is what.
Can you explain it again, sir?
Okay, what is it?
So the last line on the previous slide, the integration.
Okay, this integration, okay. What does it mean? This integration means if we integrate it, you are picking the value x tau for a particular value of tau.
Yes, sir.
Thus, then if we keep going on doing this thing, you are adding all x tau at a particular value of tau. So what is happening then? This becomes this, okay. This becomes this figure. If this axis is your tau, for any tau, you will see that you signal you will be changing your tau, getting a value. No, this is t. You are changing your tau, getting a value. Say
Yes,
tau equal to 0, then tau equal to tau 1, another value. Tau
Yes, sir.
equal to tau 2, another value. Tau equal to tau 3, another value. Tau equal to tau 3. Because you have to integrate. The reason is what? If you simply multiply your x tau with delta t minus tau, the amplitude is infinity. But if you integrate it, then this will give you what? The value of
tau.
x tau. That's why you have to integrate, isn't it?
Yes, sir.
But that integration for a particular value of tau, it will be what? A running sum. Because your tau is not appearing at the same instant, isn't it?
Yes, sir.
So if we just, if that resolution tau is very high, then all the signal will be coming closer and it will take the shape of a continuous signal, isn't it?
Yes, sir.
Thus, in this way, we usually express our signal with the help of continuous signal with the help of weighted integral of our delta function, okay? And this will be very helpful, okay, if you want to compare it with your DT signal, okay? Consider your DT signal first. DT, then it will be very clear, okay? So you see that in our DT case, we expressed our unit step function in this way, UN. Okay, this is 1, this is 1, this is 1, this is 1, 1, isn't it?
Yes, sir.
For n equal to 0 to 1, 2, 3, 4, and it will be keep going, and you do not have value in this region, okay? And the amplitude is 0. Now, and we define our delta in continuous, okay, from this point, you have to remember very carefully that we have our another delta definition for discrete time, delta n. It is appearing at n equal to 0. But the amplitude is not infinity, okay? That means your delta n has an amplitude equal to 1 for n equal to 0 and 0 elsewhere. You understand the thing?
Yes, sir.
But this is not true for continuous time case, because continuous time case magnitude of your delta is infinity, but area under delta equal to 1. So where the area is very important. Now in that sense, what you can consider, is it not, for example, UN is a sum of your, for example, if we write, I am writing the equation then explaining it. Okay, can you understand it? This is also a running sum. Running sum means they are not, your sum should is not, it will not give you a single value, okay? Rather it will give you a sequence of numbers. The reason is that the location of your delta is not the same location. Okay, consider that. Okay, you have to keep it 0. Okay, 0, 0, not. Consider k equal to 0. If we set k equal to 0, then this will be equal to what? Delta n, isn't it?
Yes, sir.
Is it not this thing?
Yes, sir.
Okay, fine. For k equal to 1, it is delta n minus 1, isn't it?
Yes, sir.
Is it not that delta n minus 1?
Sir,
It is a shifted version of your delta.
yes, sir.
If this is appearing at n equal to 1, if you shift it to the right by one sample, then what will happen? It will be equal to delta n minus 1, isn't it?
Yes, sir.
So if we want to take k equal to 2, then it would be equal to n minus 2. What is n minus? So this is your delta n minus 2, isn't it?
Yes, sir.
So in this way, you can see that if we have a delta function in our discrete domain, then this delta function can be shifted and added together to generate that unit step. Then this would be the equation for unit step. It is something like integration. Now extend this thing. Is it clear to you now?
Yes, sir.
Okay. Now let us go in the reverse way a bit. Okay, this is your UN. Now consider we have another, we are shifting this UN to one sample. To the right. This is 0, this is n equal to 1. This is n. What is this? Is it not UN minus 1?
Yes, sir.
Fine. Then if we subtract these two figures, what will happen? What you will get?
There will be already a value at t equal to 0.
Is it not that thing?
Yes, sir.
So this is your delta n, isn't it?
Yes, sir.
According to this definition. So you can write another equation then there. U n minus u n minus 1. That means two consecutive, you are shifting ones, then this would be equal to delta n. This is your difference equation. Okay, you have learned finite difference or difference in your numerical technique. Okay.
Yes, sir.
So this is the difference, because you see that differencing means what? You have two consecutive in the continuous domain. If we have our function and we know the value of the function at two consecutive instant of independent variable, say this is x, and divide it by x, and we set your limit, for example, del x tends to 0. Is it not that the definition of your df by dx?
Yes,
Learn?
sir.
Okay. That means you need two consecutive values separated by a distance del x. Then you are calculating the slope of this portion of your curve. In the case of discrete domain, we do not have time or independent variable. In this case, what we are going, or n is the index that is independent variable. And the difference between these two consecutive n is always equal to 1, isn't it? If all sample exist. What is the difference between this sample and that sample in terms of n? Is it not one sample point different?
Yes, sir.
So in this way, this is actually the derivative in discrete domain of a discrete sequence. It is called first order derivative. The reason is that we are taking only two samples, because this derivative can also be taken are calculated numerically by using three different techniques. One is called backward difference, another is called forward difference, the third one is called
Central divided difference.
central difference. Yes, so there is many techniques. This is what the most simple case of forward difference of first order. So in this way, we can go from unit step function to delta function and delta function to unit step function. In the same way, if we integrate our delta function, you will get the unit step function that you know. Now, we are generalizing it. We want to generalize it, okay? Consider that we have a sequence xn. You know that your sequence can either be expressed as for example, a sequence of numbers in this way, or by figure, isn't it?
Yes, sir.
Something like this. And your 0 is there, okay? In reality, when your x values are given numerically, then an arrow will be there beneath a number that will indicate that this is the location of n equal to 0. Otherwise you cannot operate or manipulate the signal. Now, or if your figure can be given in this way, okay? At x equal to say -2, n equal to -2, you have a say value of your signal this. At x equal to n equal to -1, say you have a value this. N equal to 0, you have a say value this. Similarly, you can assume value for other instances. Okay, so that no value is there. So this is your signal. Now this value is x0, isn't it?
Yes, sir.
This value is x2. This value is x1. This value is x minus 1. This value is x minus 2. Okay. Now tell me, if we are having, for example, say another sequence of unit step. Here is one, another unit impulse. Another is one, another is there, another is there. Okay. This is that 0, 1, 2, minus 1, minus 2. If we multiply them together, will there be any change in your signal?
No, sir.
The reason is what? The reason is that amplitude equal to 1, isn't it?
Yes, sir.
So that multiplication can be expressed as a sequence x that will be equal to what? X minus 2 delta n plus 2 plus x minus 1 delta n plus 1 plus x0 delta plus x1 delta n plus n minus 1 plus x2 delta n minus 2. Isn't it?
Yes, sir.
Will that change any signal? So amplitude? No.
No, sir.
So if we add them, can we express this in this way then? Can we express it?
Yes, sir.
Yeah?
Yes, sir.
Fine. Is it not a very similar expression of integration that we have seen earlier?
Yes, sir.
The what conclusion can be done? This is one of the important use of impulse function in continuous time and discrete time. Okay. What is the in conclusion? What can we do in the case of continuous time signal? We can express the signal as a weighted integral of impulses. Similarly, if we have a discrete time signal, that discrete time signal can be expressed as a weighted sum of impulses, isn't it? The weight factor will be the magnitude of your signal at the location of delta, because xn, xk is the magnitude of your signal at the location of your delta. This delta is located at n equal to k. Okay, that means your generalizing is that if this is your n, this is the location of k, then at this location your value of your signal is xk delta n minus k, isn't it?
Yes, sir.
And you are just changing your k from this region to that region and adding them up. Then what you will get? You will get a sequence of numbers, something like this, okay? Not a sum. It cannot give you a value 5, 6, 7 or something like this. Rather, it will give you a value of this type of, this addition means not you are adding these two together, because these two things are located in a
Different points.
different order. Okay, eventually you will get actually a sequence like this. So in this way you can see that any discrete time signal can be expressed as a weighted sum of impulses. Okay. Now we will be dealing with another issues. Okay, I am now not showing you slides. Okay, all things are there in your slide. I hope you will understand it. Okay, no problem. Because this is, if I show it to you, it will be very easy to understand. Now we have to manipulate our signal. Okay, sometimes we can prepare our signal with the help of these two unit step signal that we have learned. For example, UN, another is UT. Okay, tell me that if you want to, for example, prepare this signal with amplitude equal to A, duration equal to T, say this is a signal XT. Is it continuous or discrete?
So continuous.
Continuous. Can we prepare this continuous signal with the help of this unit step?
Yes, sir, we can.
How?
So at t equal to 0, there will be a unit function, and at t equal to t, there will be a
For example, for example, at t equal to 0, we'll have a step function with amplitude A, not unit, because the amplitude is A, isn't it?
Yes, sir.
And this will be equal to A ut. Then you have to shift your step at this location T with same amplitude, okay, will be equal to A. This is your A u T minus T.
T.
Then you have to subtract them together, okay? Then what will happen? Your xt would be equal to A ut minus A u T minus T, isn't it?
Yes, sir.
And that is equal to A ut minus u T minus T. Okay, so this is actually a pulse of unit amplitude. Sometimes this type of function is called window function. Pulse function is sometimes called window function. We will deal about it later, okay, when the relevancy will come. Now this is for your continuous time case. If we have a discrete time case, we want to prepare a discrete time pulse of finite duration, then can we do that in the same way? This is in UN.
Yes, sir.
Then if we shift, for example, UM to this number of subsamples, say, something like this, where we are shifting, this is your n equal to 2, okay? We are sampling 2 samples. Then if we subtract them, then what will happen?
Only the first two value will appear.
Yeah, UN minus UN minus
2.
2. Then only these two values will be appearing in our signal and it becomes a pulse. Okay?
Yes.
Similarly, if we change the value of n, the duration of your pulse will be set in this way. Then in this way, you can prepare a pulse type signal using 2 unit step. But not only pulses, we may have our signal something like this. Okay? Consider this. We have a triangular pulse. Have you, for example, encountered this type of operation earlier? For simplicity, let us consider the duration is 1 and amplitude is equal to 1. And this pulse mathematically equal to what? Your xt equal to what?
T from 0 to 1.
From 0 to 1 and it is 0 elsewhere, isn't it?
Yes, sir.
Okay, how can we prepare this signal? If you want to prepare this signal, you need a function something like this, isn't it?
Yes, sir.
Then we will be defining another function of first order type T, this function, okay? With amplitude equal to 1, we call it RT is equal to T ut. and that value, this is for example implied that when we multiply a pulse or any signal with UT, then the remaining side of the signal will be equal to 0, isn't it? Because UT is extending from 0 to infinity. This signal, do you know the name of this signal?
The ramp function.
This is called ramp signal, okay, R-A-M-P. Ramp means a vertical slope, okay, slope signal. Now, why we need this? If someone will write this thing, he need not to write it, okay? But if someone will write, for example, do not use this UT here, then this become undefined, okay? Because then this portion of the straight line can be taken into consideration there. For this reason, either you have to multiply it with UT or you have to explicitly define it in your time, okay? So we are using this thing to define our ramp. Now, if we want to find, for example, this portion of your ramp out of this signal, this portion at T, we want this, okay?
Yes, sir.
Then how can we do that? If we multiply, for example, this signal by using a pulse, something like this, with duration equal to 1 and amplitude equal to 1, your signal will be this, isn't it?
Yes, sir.
Then we know that the equation of the pulse is UT minus U.
T minus 1.
T minus 1. So this pulse, this equation XT, then can again be expressed as what? XT would be equal to what then?
XT UT.
T UT minus U T minus 1, isn't it?
Yes, sir.
Okay, this is one way to do that. But we may have some other ways to do it, okay? Consider this thing, okay? Well, I will be giving some hint, but rest of the things should be done by you. So this is our ramp. In order to prepare this pulse, how can we do that? Consider this is U1 time unit. Then what you can do okay, you can draw a line here, something like this, okay, red line. Then in order to prepare, for example, we need this portion. Then what you need to do, you have to discard this portion and discard this portion, isn't it?
Yes, sir.
So how can we discard it? For example, discard it means you have to subtract this region.
So we can subtract.
This one region in this way. At this location, you define another ramp, shifted ramp. Okay.
Sir. Yes, sir.
Then if we define the shifted ramp and add this thing together, then what you will get? This
There will be a step.
the region 1 will be eliminated.
Yes,
and
sir.
Region 1 will be eliminated. You will be having this curve, isn't it?
Yes, sir.
Then again you can just use another, for example, thing there with amplitude equal to 1 negative, okay, something like this, okay? You add them together. That will eliminate this region, isn't it?
Yes, sir.
So in this way you can prepare this signal also. But let us show that this operation and the previous operation using this pulse are same. So your xt would be equal to what then? Xt would be equal to TUT, the ramp, first one. Then you have shifted your ramp to T minus 1 to UT minus 1, because this should be, of course, should be written UT minus 1, otherwise it become undefined in this region, okay?
Yes, sir.
Okay, plus. Then you have to
Won't it be minus?
minus, yes, it will be minus. Very good. So this is minus, then it will be another minus will be there, UT minus 1. Okay. Then you can easily show that this equation and this equation are exactly same. So in this way, because one term will be cancelled. So in this way, any signal can be generated with the help of this tree in the first order. But if you have a signal that is exponential or some other form, that is not that much easy to generate in this way. Okay.
Yes, sir.
So let us go back to our slide. So everything, some other things are there. I have already touched it. Try to have a look. If you have any problem in understanding this letter, you can talk to me. Okay. Now we only considered our earlier slide. We considered continuous RAM, but discrete RAM is also possible in the same way, like your unit step. You see that in this case, the equation for your discrete RAM will be something like this. Okay. Because you see that if we sample this signal at regular interval of time, this magnitude will be increasing linearly, isn't it? For this
Yes,
reason, equation will be this. Okay, at n equal to 1, value will be equal to 1, n equal to 2, value will be equal to 2, something like that. That will take the shape of a discrete RAM. Now this is an example, okay, where the same technique that we learned earlier is used to generate an arbitrary signal. Okay, your dotted lines are the elementary signal that have been used to prepare this dark or solid curve. Okay, try to verify it by your own. It doesn't need any mathematics. Simple visualization and translation of your curve. Okay.
Yes, sir.
Again, the something is coming that many of you do not like. Is it true?
No, sir.
No. So all of you like this thing, computer programming?
Yes, sir.
I don't think so. Because I did not see any, for example, of your activities that only few are using computer, others are not. Okay, do you understand this program? Simple function, how to generate this signal. Do you have any idea what will be the shape of this signal? Can you draw it? Because we have two ways to express a signal, either mathematically or figuratively. Can you draw it?
Yes, sir.
Okay, you try to draw it. Okay. Then this is your function. You can have this function run by yourself, or you can write it in your own way. And you can visualize it by using a MATLAB or any other program. Even nowadays, students are learning Python. Okay, how many of you are learning Python?
Yes,
Have you
sir.
heard about the name Python?
Yes, sir.
So nowadays, you see most of the students, even they did not go to the school, even colleges. Okay, they can program in Python. Nowadays, okay, no degree is needed to learn computer. Okay, many outsourcing of students, many people are doing outsourcing. They do not have any degree. Okay, they do not need any degree actually. If you have any skill in programming, you know the logic. That's it. So try to learn Python. Okay, Python would be a what do you call a standard within few days. Already many things are, because it is open source. Many people are doing on it. Many resources are available. You can use them in your purpose. Okay. So you try to run this program and see how it works. Okay. This is also another piece of program where this figure is generated. Okay. You see that the original signal is this. What is the difference between original signal and the later one? Later is shifted, okay, by 1 unit. And the third one is it is compressed in time. And the fourth one is it is shifted and compressed, okay, by using simple operation of MATLAB, okay. Try to verify them. Or even you can write this thing by your own way and a smarter way, okay. Now we will be at this point. Let us stop our introduction with some signal. We have many other issues regarding those signals, but we will be dealing with, we refer to our system when we'll be going to higher topic, okay? Because this is the preliminaries. For this reason, many of the things that we are discussing here may not be visible to you at this stage. So when we have a system is actually an interconnection of operations. Because as I have talked to you earlier, that when we design a system, no matter whether electrical or mechanical, whatever it may be, you will need some input and you will have some output depending on which output you design. Accordingly, you have to design your system. Mathematically, what it happens that your system is actually operating a signal to give you the desired output, isn't it? That operation may be simple and even it can be complicated. That operation needs arithmetic, that operation needs logic. All operations could be there in that system. Your system can have a single component or your system can have multiple components connected in different topologies. But mathematically, if we represent our signal system as an operator, then in this book that we are following, they use this notation to represent your signal in a simpler way. You have a signal that has an operator, they're calling it H operator. Then we will be getting an output YT. That output is operated. It is written in this way. This curly bracket shows that an operation is there. We do not know yet what operation is being done on XT, but it will be depending on your signal. Okay, similar case is can be there for a discrete time case. One of the operator is shown there. Okay, this S operator is called time shift operator. It will have an index. So if K index is there, what operation is being performed by this system?
Shifted the signal.
Okay,
to,
it is shifting the signal by K samples to the right.
Yes, sir.
Similarly, if your K is negative, it will be shifting to the
negative side.
left. Okay, so in this way, not always negative. The reason is you do not know where your present position is. Okay.
Yes, sir.
So the general expression should be to the with respect to the present position, either to the left or to the
Right.
Right.
right. Okay. Okay, now we consider, this is also an example, okay? Do not find a logic behind it. Just at this stage, try to understand that how the individual pieces of subsystem could be connected together to build a whole system. Okay, consider that we have a simple thing we need to do by using a system. What is it? It is of course a discrete time system, isn't it?
Yes, sir.
Fine. In this discrete time system, what operation is being done? You see that at n equal to 0, at any instant n, it is taking a value xn. You can call it present value.
Yes, sir.
And then you have a next value, then you have next another value. Here it is simply taking 3 values of a sample and adding them together and
divided by 3.
divided by 3. That means it is simply, it is not a running sum. Be careful about that. Okay, it is not a running sum. It will be an averaging technique. Okay, this technique is used in many of our purposes. It is called moving average type filter. In many of our purposes to smoothize our signal to eliminate the noise. Okay, unfortunately we consume 15 minutes to set up our system. Then we could have some more additional time to discuss about this filter. I will discuss it later in some extension. Okay, how this simple averaging operation can smooth your noisy signal to a smoother one. Very simple. Okay. So how, if you want to implement it, for example, if you want to implement it by using a system, then what particular thing is being done there? You need 3 samples. But if xn is your input, you need a shift operator to shift one sample. You need another shift operator to shift further, isn't it?
Yes, sir.
Then you need an adder to add them. then you need a multiplier to multiply with a factor 1 by 3, isn't it?
Yes, sir.
So you have two possible ways to do that, okay? One possible way is this: your input is there, it is being fed to a shifter with index equal to +1, making you shift one time unit to the right. Another, and further it is, this shifted signal is then again applied to another shift with index 1. It is further shifted to one sample. Is it okay?
Yes, sir.
So the output of the second shifter will be equal to 1 minus 2. Then you have a summer. At that summer you tap your input. This is your input. You tap the output of your first shift. This is an xn minus 1. Then you take the output of your last shifter. It will be an. So this output of this summer is simply xn plus xn minus 1 plus
Xn minus 2.
then you have a multiplier there, then it is your output, okay? The same implementation can be done in this way. Now you can ask me that which is the beneficial, okay? Many other things are there you have to study regarding the performance of your system, right? The thing is that you know your computer programming because you have attended a computer programming course. You see that same problem can be solved or programmed in many different ways. And you will see that the computational time and the error or efficiency of computation will be depending on which algorithm you are using, isn't it? Yes or no?
Yes, sir.
For this reason, you need your numerical method. Many methods are there to solve a single problem, isn't it?
Yes,
For
sir.
example, for solving a differential equation, how many methods you learned? How many techniques you learned in your numerical? Because you finished this course a few days ago. What are the method you learned for solving ordinary differential equation?
Sir, second order Runge-Kutta method, fourth order Runge-Kutta method, Euler method.
Very good. We have lots of methods, isn't it? Did you understand that why we need so many methods to solve a particular problem?
Yes, sir, some are more complex and some are more accurate.
This is very general thing, okay? The complexity and accuracy is correct. But complexity means very, okay, it doesn't mean that your equation will look complex, okay? Your equation will behave in a complex way. Although your equation will be looking very simple, but it will be behaving in a very complicated way, okay?
Yes, sir.
For these reasons, that complexity should be depending on which type of system you are dealing with. And accordingly, if you cannot set your algorithm, then as you know that your differential equation, you are simply integrating, okay, to get your value back. That integration algorithm should be set in such a way that error should be minimum at or reducing in each step. Otherwise, what will happen? As you are adding your solution in every time step, if your signal, if your algorithm is poor in performance, then what will happen? At every step, it will be giving you an error, and that error you are adding at every step, and eventually you are amplifying the error as it progressed in time in computation. And eventually what will happen? Your total solution will be getting unstable and useless. Although the algorithm is very simple. You have learned Euler method. What book you followed?
Sir, hello.
Sorry?
Sir, can you repeat?
Which book, textbook you followed for numerical method? No idea.
Yes, sir. So the Chapra book, sir.
Stephen Chapra, okay? Stephen Chapra's book is one of the famous book. He have written two books, okay? One is simple numerical method, another is advanced numerical method by using MATLAB. Both of the books are the most elegant books followed. Almost in 90% of the universities are following this book, okay? It is dedicatedly written for scientists and engineers. Lots of engineering examples are there of practical importance. Okay, where you have seen that in the Euler algorithm, two scenarios were discussed there. Okay, a simple first order equation. By choosing the algorithm, you will see that in one algorithm it is stable, in other cases it becomes unstable. Try to figure out where it was. And that's why a definite class of differential equations are there that it has to be handled by a specific type algorithm. So we need different technique. Performance of all algorithm will not be same. That is not equally applicable for system configuration. System configurations are also algorithmic approach. So after having the system configured, you have to study the stability and performance of the system. That is another branch of learning and topic. We will be introducing this thing when we will be dealing with system after having this introduction delivered to you. Okay, inshallah. Then these are the possible things. System can be concatenated together like cascade, or it can be parallel. Even your system can have feedback. Have you learned about feedback system earlier?
Yes, sir. In the communication course, sir.
Communication course. Okay. Don't in other course if feedback is needed?
Op-amp, sir, electronic.
Op-amp, sir.
Yes, sir. Control system.
A control system you need. Did you study control system? You started now.
Sir, we are studying it, sir, in 3-2, sir, in this semester.
Okay, very good. Okay, control system is very, very interesting and most interesting course, I would say. Try to utilize it. Okay, get stuck from it. You will see the control system. Mechanical engineers are also learn the same control system. What book your teacher suggested?
Sir, the book is a control system designed by Norman.
Nice.
Norman, okay. But my advice is, along with the book your teacher is following, try to manage this book, okay?
Sir, another book he is following is, sir, Modern Control Engineering by Katsuhiko Ogata.
Katsuhiko Ogata. Ogata's book is very tough, okay? And we also learned Ogata's book when I was at your age, okay? You can easily consider that this book a very classical book. Even we have a book written by Dorff, okay? But try to
Norman S. Nice.
try to use this book, okay? Or follow this book for your understanding. The name of the book is I cannot remember it clearly, but
sir, are you suggesting the Nice book, sir?
Yes, both books.
Sir, yes, sir. This is the books sir will be following mainly.
The Nice book, okay?
Yes,
Isn't
sir.
it?
Yes, sir.
That is a very, very important and good book, okay? You will see many, many interesting things there, okay? I love this book. I still read this book, okay?
Yes, sir.
And I was planning to, for example, teach some of this control course, but they are teaching, so I did not go there. Control is very, very important thing. Very, very important. Very, very important. I am reiterating it. Okay, be careful about this. But feedback is not something like this used in only communication, in only electronics. Okay, even if you want to design an amplifier, you need feedback, isn't it?
Yes, sir.
Okay, then you need feedback. If you design to use a controller, you need feedback. In many ways, you need feedback. Okay, your feedback system is another. Feedback system stability concern is very big used, because if you want to, for example, design an oscillator, which type of feedback you need to use? What is the gain of an oscillator? Theoretical gain?
Sir, positive feedback will be needed in an oscillator.
Theoretical gain of an oscillator is what? Because your amplifier will have a finite gain. Okay. The reason is that if you draw your frequency response, have you drawn frequency response ever in your learning?
Yes, sir.
That this is your frequency, this is your gain in dB. Okay. Usually this scale will be in logarithmic. Why logarithmic?
Because the frequency range.
Frequency range is very, very high. Exactly. Very good. Because your frequency can vary from 1 hertz to even 1 megahertz. Isn't
Yes,
it?
sir.
1 millions of hertz that you cannot plot in a linear figure. For this reason, we use this axis logarithmic. So your frequency response is usually plotted in semi-log paper, isn't it?
Yes, sir.
Your independent axis will be logarithmic, vertical axis will be normal in dB in general. You will see that your amplifier will have a frequency response, something like this, okay? Your gain will be remaining constant within a certain region, but it will drop in this region. This is your upper cutoff region, lower cutoff region, this is your upper cutoff region, like a band pass filter, okay? It will operate a band of frequencies, isn't it? Within this band, for example, if you want to design an amplifier for your voice signal, what should be the bandwidth minimum? What is the range of your voice signal frequency?
2 to 2000 hertz.
Okay, then try to find a design of voice amplifier, okay? Then you will understand the consequences of frequency and design in an amplifier. But if we have an oscillator, you see that frequency response curve will be something like this, okay? It will be, theoretically, you will have a frequency F0 oscillating frequency. And your bandwidth is almost 0. If your bandwidth is 0, then what will be the thing? Then eventually the gain of your amplifier needs to become infinite, okay? And your feedback should have positive values, positive feedback. Otherwise, amplifier, what we are calling, oscillator cannot be designed. Have you seen this type of equation? A divided by A is gain 1 plus beta into A.
Yes, sir.
And from this thing, we can design a criteria that this quantity should be equal to -1 for oscillator ideally. This is called Barkhausen criterion. Barkhausen. Have you heard this name?
No, sir.
No, sir.
Then what have you learned then? Because in order to use feedback amplifier, this is the basis from where you have to start with. Barkhausen criterion, okay? Try to learn about it. Even those who taught you, try to get some idea from them.
Okay, sir.
Undergraduate basic is very important to teach student, okay? We do not need, for example, that much research oriented something to teach it. But the basic of thing that should be very clear, those who are clear in basic, they can clear others basic, okay? That you have to be very careful about. So do not keep any hole or any void in your learning, no matter to what extent you are learning, but learn it perfectly, okay? Master of jack of all trades, but master of none. That logic is not applicable for engineering. You got my point?
Yes, sir.
Rather, you think in the reverse way. You need not to be jack of all trades, okay? You select few topics and try to be master on them, okay?
Yes, sir.
Only when you can work. So that is why we are planning to set our OBE, okay? Our learning objective. Not all students will acquire all objective, but the objective that you are focused on, you have to make it very, very clear, okay? Now the system, another system properties is there. I will be taking another 2 minutes and then I will give you percentage. Or let us finish this thing here, okay? Because prayer time is there, some of you could pray.
Yes.
As you are lagging around 5 or 6 minutes, I will cover it up in the next day. Take help of section, the earlier section who recorded my lecture, okay?
Yes,
and you will find the complete set there, inshallah. Okay, that's it from my part today. I am taking your personal now.